Hello everyone. Welcome to our discussion on Chapter 1, Introduction to Non-Parametric Statistics, part of your Advanced Statistics course. I'm Mildred A. Sebastian, and I'll be guiding you through the key concepts, important differences between parametric and non-parametric methods, and how to use SPSS to conduct non-parametric analyses. Before we begin today's lesson, let's take a look at what you'll be able to do by the end of this chapter. These are our learning outcomes, or goals, for understanding non-parametric statistics. 1. Explain the non-parametric statistics. In this chapter, you will learn what non-parametric statistics are, how they work, and what makes them different from other types of statistics. 2. Identify scenarios in which parametric statistics are preferred over non-parametric statistics. Sometimes, parametric methods are more powerful if certain conditions are met. You'll learn when it's better to choose parametric tests instead. 3. Understand the difference between parametric and non-parametric statistics. By the end of this chapter, you should be able to clearly tell the difference between the two types, how they're used, what they assume, and what kind of data they handle. 4. Recognize when to use non-parametric statistics. By the end of this chapter, you will be able to decide when non-parametric methods are the better choice, especially when data is messy, non-normal, or limited. 5. Get acquainted with the basic concepts of non-parametric tests. Finally, you will learn the names and purposes of some common non-parametric tests, like the Mann-Whitney test, chi-square test, or Wilcoxon signed rank test, and when they're used. So by the end of this chapter, you won't just know the terms, you will be confident in choosing the right type of statistical test based on the data you have. Let's get started. Before we go further, let's warm up with some important review questions. What's the difference between mean, median, and mode? Think of these three as ways to find the center or the most common part of a group of numbers. Mean is just the average. You add all the numbers and divide by how many numbers there are. Median is the middle number when you line up all the numbers from smallest to biggest. Mode is the number that shows up most often. How do we calculate variance and standard deviation? These two help us understand how spread out the data is. Step 1. Find the mean, average, of the data. Step 2. Subtract the mean from each number to find the difference. Step 3. Square each difference. Step 4. Find the average of those squared differences. That's the variance. Step 5. Take the square root of the variance. That's the standard deviation. The more spread out the numbers are, the bigger the variance and standard deviation will be. And most importantly, what does standard deviation tell us? The standard deviation tells us how much the numbers vary or move away from the average. If the standard deviation is small, the numbers are close together. If it's large, the numbers are spread out. So if you're analyzing test scores or sales data, standard deviation helps you know if everyone did about the same, or if results were all over the place. These questions help set the stage because understanding how we summarize data helps us understand when our assumptions, like normal distribution, might not hold. And when they don't, non-parametric stats come to the rescue. Non-parametric statistics are used when we don't want to make strict assumptions about the data, especially about how the data is distributed. In many traditional or parametric statistics, we usually assume the data follows a normal distribution, like a bell curve. But what if the data doesn't follow that shape? Or what if we don't know anything about the population? That's where non-parametric methods come in. They don't assume the data follows a specific shape or distribution. Why are they important? They're more flexible. They work better when your data is skewed, has outliers, comes from a small sample, or is not measured with exact numbers, like rankings or categories. Think of non-parametric statistics as the go-with-the-flow tools of statistics. They're good when you're unsure about the structure of your data. So, to sum it up, non-parametric statistics are like the rule breakers of statistics. They don't follow strict assumptions and can be used when we have limited or unusual data. Any questions so far? Or have you seen examples where the data didn't seem to follow a normal pattern? Alright class, let's continue with the lesson. This slide highlights one of the key characteristics of non-parametric statistics, flexibility in data types. What does that mean? It means that non-parametric methods work well with many different kinds of data, even if the data doesn't meet the usual requirements needed for other kinds of tests, like parametric tests. Why is that useful? Let's say we have ordinal data, like rankings, first, second, third place. Categorical data, like types of fruits or favorite colors. Or even data that's not normally distributed, not shaped like a bell curve. We can still use non-parametric methods to analyze it. This makes them really flexible and helpful, especially when working with real-world data that isn't always neat and perfect. So in short, non-parametric methods don't need your data to fit into a perfect box. They're like the all-purpose tools of statistics, ready to work with whatever you've got. Let's keep going. This slide talks about another key characteristic of non-parametric methods, minimal assumptions. What does this mean? It means that non-parametric methods don't expect your data to follow any specific shape or pattern, like the normal bell curve. In many parametric tests, like t-tests, the data must be normally distributed, a nice, even curve, have no extreme outliers, and meet other specific rules. But with non-parametric tests, we don't need to worry about that. Why is this helpful? Let's say your data is skewed, maybe everyone scored really high or really low on a test. Has outliers, one or two numbers are way off. Or just doesn't fit a normal distribution. Non-parametric methods still work well. That's why we say they make minimal assumptions about the data. In simple terms, non-parametric tests are like easygoing tools. They don't expect perfect data and can still give you good results when your data is messy. Alright class, let's look at another key characteristic of non-parametric statistics. Rank-based or sign-based analysis. What does that mean? Instead of using the actual values in the data, many non-parametric tests use ranks, which means we order the data from smallest to largest and assign numbers based on their position. Or signs, which means we only focus on whether the value is positive, negative, or zero. We do this instead of using the raw numbers directly. Why is that useful? Using ranks or signs helps to reduce the impact of extreme values, called outliers. It also helps when the data is not normally distributed or is on an ordinal scale, like rankings or survey responses. For example, if we had test scores like 55, 60, 100, 62, and 61, that 100 might throw off a regular average. But if we rank the scores, first, second, third, etc., we reduce its influence. So in short, non-parametric tests don't care as much about the exact numbers. They care more about how the numbers compare to each other. This makes them great when our data is messy or doesn't follow normal rules. Now let's talk about where we actually use non-parametric statistics. This is the real-world part of our lesson. Applications of non-parametric statistics. Where are these methods used? Non-parametric statistics are very popular in fields like biology, psychology, social sciences like education, sociology, etc. Why? Because in these fields, we often deal with small sample sizes, messy or unusual data, or data that doesn't fit the normal distribution. Example. Let's say a psychologist is studying stress levels among 10 patients. That's a small group, and the stress scores might not be evenly spread out. A non-parametric test would be more reliable than one that assumes perfect, normal data. So in simple terms, non-parametric methods are used when data is limited, weird, or doesn't follow the usual rules. They're like the go-to tools for researchers when things aren't ideal, which is often the case in real-life studies. Alright class, let's take a moment to compare two big types of statistical methods. Parametric versus non-parametric statistics. This chart gives us a side-by-side view so we can clearly see how they're different. Let's focus on the first point of comparison. Assumptions about data distribution. On the left, parametric statistics. These methods assume that the data follows a specific shape, usually the normal distribution. That's the familiar bell curve you see here. The data is nicely spread out with most values around the center, mean. This works well if your data really does follow that shape. On the right, non-parametric statistics. These methods don't assume any specific distribution. The data can be skewed, have outliers, or be irregular, and that's okay. That's why you see that slanted orange line on the graph. It shows that the data doesn't need to fit into a perfect bell curve. These are useful when we don't know the distribution of the data or when it's clearly not normal. So to keep it simple. Parametric, I expect a bell curve. Non-parametric, I'm okay with any shape. Now let's continue comparing parametric and non-parametric statistics. This time, we're focusing on the types of data each method works best with. Point of comparison number 2, types of data handled. On the left, parametric statistics. Parametric tests work best when your data is quantitative, that means you're working with numbers you can measure, like height, temperature, or test scores. These numbers should also be on a scale, like interval, where the difference between values matters, or ratio, which has a true 0 point, like weight. Plus, the data should follow a normal distribution, that familiar bell curve we talked about earlier. So, parametric is great for nice, clean, numerical data that behaves predictably. On the right, non-parametric statistics. These are more flexible. You can still use them with quantitative data, but they're especially helpful when your data doesn't meet the strict rules of parametric tests. Even better, they can also handle qualitative data, like nominal, categories like gender or color. Ordinal, rankings like first, second, third. As well as interval and ratio data. So, non-parametric works with almost any kind of data, not just numbers. To put it simply, parametric methods are a bit picky, they want specific types of numerical data. Non-parametric methods are flexible and can work with both numbers and categories. Let's move on to the third point of comparison between parametric and non-parametric statistics. This one is about statistical power and efficiency. What does statistical power mean? It simply refers to the test's ability to detect a real effect or difference when one actually exists. Think of it like this: if you're trying to find out if a new medicine works, a test with high power is more likely to say, yes, it works, if it really does. Parametric statistics. These tests tend to be more powerful and efficient, but only when their assumptions are met, like normal distribution and scale data. That means they have a higher chance of detecting true differences or patterns in the data. So when your data meets all the right conditions, parametric tests are usually the best option. Non-parametric statistics. These are a great backup when the data doesn't fit the parametric rules. While they're sometimes less powerful under ideal conditions, they can actually be more powerful than parametric tests when those conditions are not met. In other words, non-parametric tests might not always win in perfect situations, but they do better when real-world data is messy or unusual. So to sum up, parametric, stronger if everything is just right. Non-parametric, a better choice when things don't go as planned. We're now looking at the last 2 points in our comparison of parametric and non-parametric statistics. 4. Approach to analysis. 5. Application scenarios. Let's go over each one clearly. Point 4. Approach to analysis. Parametric statistics. These methods rely on parameters, like the mean and standard deviation, to perform hypothesis testing. This means they depend on certain assumptions about the shape and structure of the data. Non-parametric statistics. These methods are often based on ranks or signs. That means instead of using the actual data values, they may use order or direction, like whether values are higher or lower. So, parametric methods use actual numbers and formulas, while non-parametric methods focus more on order or trends. Point 5. Application scenarios. Parametric statistics. Best used in controlled research environments, where the data follows all the rules. The data needs to be interval or ratio type, and the assumptions like normal distribution must be met. Non-parametric statistics. Great for exploratory research, fieldwork, or any situation where things might be unpredictable. Works well when you have non-standard data types, like rankings, categories, or unevenly distributed numbers. So, if you're doing research in a lab with clean data, parametric tests might be ideal. But if you're surveying people in the community or working with odd or messy data, non-parametric is often the better choice. In summary, parametric, precise and powerful, if conditions are right. Non-parametric, flexible and useful, especially when conditions aren't perfect. To wrap up, we explored the fundamentals of non-parametric statistics, a flexible approach that allows us to analyze data without assuming a specific distribution. We compared it with parametric statistics, which require stricter conditions like normality and scale-level data. We learned that non-parametric methods are especially useful when dealing with small samples, non-normal data, or ranked and categorical data. By understanding the differences, applications, and strengths of each method, you are now better equipped to choose the right statistical approach based on the nature of your data. Remember, there's no one-size-fits-all, your choice depends on the situation and the data you have. Let's continue applying these ideas as we dive deeper into specific non-parametric tests in the next lessons. Thank you.